This end of the school, I thought first I'll give you a glimpse. We have selected some set of topics which we feel is the current trend in parameterized complexity. And these topics are tree width, what I call important cuts. Then you will see some advanced kernelization. And some what I call modern hardness reduction. And finally, we will see some lectures on matroids-based algorithms for this. But before we go further, what we called basic part of the school, which is what try to cover in last 1, 2, 3, 4, 5, 7 lectures. So just to give you an overview what we did actually. So we started with simple algorithm for vertex cover, and what was the idea of this algorithm? It was very simple. Pick an edge, okay? Either this vertex goes into the solution or this vertex goes into the solution, or basically either V is in the solution or N of V is in the solution, and this gave you some recurrence of form something, and you analyze that to get some this kind of algorithm, right? So this is the first basic technique we learned. Second thing which we learned in that lecture was a 3k power k algorithm for feedback vertex set. And what was the algorithm? Algorithm was very simple. It said, let's do some normal preprocessing, delete vertex of degree at most 1. If you have something like this, then x, y, z, then do x and z, and do some sort of short circuiting so that a graph has, such that the graph has what do you call minimum degree 3. And the crucial lemma then we proved that if we sort these vertices in increasing order of degree, like v1, v2, vn, where d of br, like d of v1 is greater than or equal to d of v2, blah, 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 then what we showed, look at the first 3k vertex, there is no way any feedback vertex set of size at most k cannot intersect with this. And the idea for all of this algorithm, the other way of looking at feedback vertex set or many of this problem is that basically you want to delete vertex such the graph becomes sparse, right? In vertex cover it is independent set. Here, so basically it's very likely that if a vertex has a high degree, you might need to cover. Now the point is, the basic idea of the proof was that if you look at any 3k vertex, if it does not intersect, then all the high degree part of your vertex, which is a part of the feedback vertex set, is here, and that should cover certain set of degree, but then this first k, next k, next k should also cover certain amount of degrees. And that was the basic idea of coming up with 3k to the power k algorithm. Okay, so if you just do the maths, this is what it was. So we saw a couple of examples of branching algorithm, and then we moved to kernelization. And there, the technique 1 which we saw is called high degree rule, right? What was the high degree rule? Basically, we employed this high degree rule for vertex cover. We employed this high degree rule for feedback arc set in tournament. It's just that the way we used was very different. In vertex cover, we said, hey, if here is V and there are k plus 1 guys, neighbors, if you don't pick, then this k plus 1 must go into the solution. For feedback arcs in the tournament, we first reformulated this problem as reversal problem. Then we said, if there is an arc which participates into k triangles, then this arc must be turned. And that was the basic idea of the whole this thing. I mean, you can go and do the maths, but that was the basic idea of these two reduction rules. So, and then what we saw was a kernel for max set. And the kernel for max set was basically guided by the following thing, which is called, actually is called crown reduction rule. And basically what is a crown reduction rule in a graph is basically you have a crown, you have a head, you have a crown, and you have the rest of the body of the king. And here head is matched into C, okay? And there is no vertex from C to R. So basically H is kind of separator between C and R, right? And then basically in most of the tricks which you will see based on crown decomposition, you can say, and C is the independent set. So what is C? This is independent set. H, there's a matching saturating H, and there's the rest of the thing which is attached only to H but not to C. And then most of the time the reduction rule is pick these H into your solution. So now you will reduce your parameter by K minus H, right? K minus H, and delete C and H. Now, for example, let's look at a very simple example of this reduction rule. Suppose I had a vertex cover and I had degree 1. I mean, is there any point of picking this vertex into the solution? It's best that I pick this vertex because it will definitely cover this and the rest. Now, this is my head, this is my crown, and this is my rest of the body. So basically, this is a generalization of this degree 1 rule which was employed for the vertex cover. And that is what is based on Hall's theorem and everything, and that is what Neil told to get you with K variables. Okay? And what else did we do in that kernelization lecture? Sunflower. Okay? So then we saw another extremal structure based on sunflower. And what did it say? It said, hey, look, if you are looking for a problem which is like hitting set and these kind of things, then basically what it said is that if I find a structure which is like core, and my set family is this, and if you're not going to pick this vertex into a solution, then you have to pick one from here. It is also a generalization of high degree reduction rule. Then basically replace your family, delete all these sets and replace this with core, and you keep doing this. And the extremal argument told you that if the family is big enough, you will always have such a structure. Okay? So if the family is large, you always have such a structure, and hence you will be able to apply this reduction rule. So when you are not able to apply this reduction rule, you have a reduced instance. So that was a lecture number 2 which we saw kernelization. So high degree rule, crown reduction, sunflower lemma. In the next part of the lectures on advanced kernelization, you will see more extremal combinatorial technique being employed to reduce our input instance. Okay? And the third lecture we had yesterday was on dynamic programming. We will see that again and again, so I will not even talk about that for a moment. Okay? Then we had another branching algorithm for vertex cover above LP. Okay? Vertex cover above LP. And the algorithm we gave for this problem had running time K minus LP and some n to the power big O of 1. It was the same vertex cover algorithm, but we analyzed in a way that in branches, so if we defined my mu as K minus LP of G, then we showed that the measure mu decreases half in both branches in a normal vertex cover algorithm, and hence the depth of this tree is 2 mu, and hence the algorithm running time is 2 to the power 2 mu, and hence 4 K minus LP. Now, there's something very nice and beautiful about this reduction which I try to tell you. Neil tried to make an algorithm yesterday for odd cycle transversal at the end. So what was the odd cycle transversal problem? Input was G and K, and what was the question? Can we delete K vertices such that, can we delete K vertices, say O, such that G minus O is bipartite? Right? This is the algorithm which Neil tried to explain yesterday. Let's see, I mean, I'm sure you did not understand that algorithm because it was towards the end. Let's see just one algorithm in one line using this 4 to the power K minus LP algorithm. So what you do, that this is an input instance, G comma K. So Neil taught you how to make reduction, like how to show something is hard using reduction. I'm going to do the other way. I'm going to give a reduction from odd cycle transversal to above guarantee vertex cover or LP, anything problem, okay? Which is parameter preserving. The reduction is very simple. You take G, you take another copy of G. Now, here you have a vertex V1, same vertex V1, you just make perfect matching between them. So basically, look at the copy of the same vertex, just add an edge between them. Now, what is the maximum matching in this graph? If I started with n vertex graph, it has perfect matching in. Now, what you can show that G has an odd cycle transversal of size k if and only if, let's call this graph H, H has a vertex cover of size n plus k, which is nothing but perfect matching plus k. Okay? The reduction is very simple. If G had an odd cycle transversal of size at most k, it means after I delete this, I have a bipartite graph, right? After I delete, look at G. Here's my O, this is my V1 and V2. And there is no edges between V1 and V2. Now, look at the copy of V1 here. Look at the copy of V2 there, right? What is that? So, they are independent set because V1 is independent set by choice, V2 is independent just by choice, and there is no edge between the same vertex, right? The only edges which we have added across the partition is between the same vertex, like V1, V1. But now, so this is an independent set here, this is an independent set here of size how much? N minus k. So what is the vertex cover of this graph? Is 2n minus n minus k, which is n plus k, right? Now you start with a vertex cover of size n plus k, and you can just go. So then you will have again two parts here, which is independent set. If I go back here, they are independent here. The only thing which is allowed is edges between them, and you can project this to get a vertex cover, to get a odd cycle transversal. Okay, so this is a simple algorithm. Just think about it. It is not very hard to prove. So there are many more such applications of this. What Neil tried to give you is 3 power k algorithm for this problem. Okay, so we saw this technique. Okay, so we saw this nice algorithm, and repeatedly I'm coming to this algorithm because these kind of measure to analyze algorithm is the current most fundamental trend in parameterized algorithms, and we will see its applications more and more even in some more lectures. Okay, now then we saw some randomized method. Okay, and then there we saw 3 algorithms. One, a 4 power k algorithm for undirected feedback vertex set, again based on the idea that, look, vertices which are in feedback vertex set, they are adjacent to most of the edges, and that is the idea we exploited to get 4 power k algorithm. And the algorithm was very simple. Do some pre-processing, randomly pick an edge, randomly pick a vertex, very high chance that this is going to be part of my feedback vertex set, repeat it k times. Then we saw this method of color coding, and we saw an algorithm for k path. And there was a question by someone that why only k path is, like why color coding is useful for k path? Because one of the main subroutine was to find a colorful path, which we saw today that if we ask for structures like click, then this just, just fails. So we cannot use color coding to find, say, k click, for example. And then finally, we saw a version of color coding, which was called chromatic coding, and this is useful to give you algorithm of form 2 power big O of k. This is generally useful for 2 to the power little o of k, right? And there was something we saw. And then we finally, yesterday we saw some iterative compression. So what was the main idea of iterative compression? Okay, it's basically, it is useful for minimization problem. Okay, and basically what we did here is that we started, suppose we are trying to apply this method on some graph problem. So we started with a graph on, say, first V1, V2, Vk plus 1 vertex. Another graph is take this, add Vk plus 2, another Vk plus 3, and last you add Vn. So basically this graph we call Gk plus 1. So basically Gi is a graph induced on first I vertex. You start with any arbitrary ordering. And the idea of this algorithm was that, hey, here, if I start with here on k plus 1 vertex, then I also have as a help function a solution of size k plus 1, right? So we did nothing more than that we gave ourselves more information to solve the problem. So the typical instance of iterative compression algorithm were input was given some graph or some problem and some solution of size k plus 1, and the goal was to compress this solution to size at most k. And the idea was that, hey, if for this smaller object answer is no, it means we don't have to go any more further. The instance itself is a no. But if we found a small size solution, then for the next guy, take the small size solution box and add vk plus 2 to be a solution of size k plus 1, which becomes our new help for a bigger graph. Again, we try to compress the solution. If we succeeded in compression, we have another help. You add vk plus 3 to have a help function for the larger graph, and we kept on going that way. At any point of time, if the answer said no, it's like I cannot find my solution for this smaller graph. There is no hope that I can find a solution for the larger graph. And so if we finally ended up here, we had our solution, or else in the process we said no. Okay, so the whole effort was to solve this problem, and we saw 3 examples. So if you don't remember any example, that's fine, but what is more important to take away message is that this is how the compression routine works. And we saw example for vertex cover, feedback vertex set, and OCT for 3 power k. Today we saw some miscellaneous method on graph minors plus ILP. ILP is still not used that much in our machinery, but graph minors are, and we will see some more examples of application of the theorem which Venkatesh taught today, that if a minor closed family, if I have a family which is minor closed, then testing whether something belongs to this or not can be done in FPT time. Okay, so I think that kind of summarizes what we more or less did, and of course the hardness reduction which Neil did some last lecture. So if you have any question up until now, please ask. Look, in some sense, on our help, I want to apply f of k, right? If my help is too big that I cannot do many things, then what's the point, right? Help should be helpful.
No, but the size that we take can be a function of k.
You could take a function of k. No one stops you from that. For example, for vertex cover, where will the algorithm fail if I started with an approximate vertex cover of size 2k? Right? Yes, it will work, but still it is some function of k which is useful. But if I start something which is a function of n, it might be useful in some cases, but I am not sure that it is. So that is why we, and in fact for many of such versions, which is called the local search version of many of these problems, they actually turn out to be hard. So I mean, if you have a help which is not a function of k, you can show in many cases that this is generally hard. Okay, so any more questions? Yes, exactly. But since what I'm starting with is a small solution, it allows me to do a local search in an effective way. But suppose if I start with a solution which is arbitrary, which is unbounded, so the neighborhood around which we might need to search a solution, it could be just too big, and hence we cannot hope to do these things in FPT time. For example, say if I have a solution of size root n. Now, even if I try to do 2 to the power root n, I cannot guarantee that this is a function of k. For example, just simple brute force to guess which vertex from here goes into the solution. Even these little, what you call, very simple procedures which be employed during our algorithm will start failing. I'm not saying you cannot, but you need some more things to know about your instance for these kind of help functions to be useful. of this, yes. Yes. Okay, so far so good. Now, what I am going to do for 4 lectures now in tree width is to introduce this nice graph parameter, but let's see how far we reach today. Okay, now I will go slow. I was very fast in the last 15 minutes because I needed to be fast. Okay. So, let's not talk about motivation. We'll come back to the motivation slide at end. After we have understood something, maybe then we have motivation. Okay, so there are going to be 4 lectures primarily with 4 parts. So first I'm going to give you, that is today's lecture, some sort of introduction and definition of what tree width are, or motivate you towards a definition of tree width. Then I will teach in the next lecture how to make algorithm graphs of bounded tree width. And third is going to be some graph properties of tree width. And finally, how we can apply the tree width as a subroutine in obtaining fixed parameter tractable algorithm or polynomial time approximation scheme. So that is a part 3. And fourth, if I will have time with my slow speed, then I will teach you how to do what is called the most technical application of tree width in parameterized algorithm is to find what is called irrelevant vertex. It's like, what do you mean by irrelevant vertex? So in kernelization also, we find a vertex to be irrelevant, right? We say, hey, this vertex cannot participate into any solution in any form, hence let's delete this vertex and we have got an equivalence instead. Now there is a methodology using tree width where we say, hey, look at the input, if it has large something, then there is some vertex or some edge which is not useful for our solution, and hence we can delete it. So this general paradigm is called irrelevant vertex technique, and you saw today in the lecture that when Venkatesh told that deleting k vertex to get a planar graph is fixed parameter tractable. How? Because look at because planar graphs are minor closed, and hence minor closed plus k vertex is also minor closed. And to show something is minor closed family, it's very easy. What you need which you need to show is that start with an instance, right? What is this instance? It is an yes instance. It means we can delete k vertex such that the graph is planar. Now look at any minor, the solution size should not increase, right? So if in the input graph if for the input graph we can delete k vertex to make it planar, then for any minor also we can delete k vertex and make it planar. And that trivially holds because, I mean, when you contract, you have more power. So like you can take down this big fat vertex into a solution and it is only going to contribute 1. So look at any minor, look at a projection of your solution to this and just take those, right? You can only reduce the solution size. Or if you do not like this way, then you say, hey, if I delete an edge, because that is the one basic operation allowed, right? Can the solution size increase? No. Any problem where we are interested in hitting something, and what are we interested in hitting in planar vertex? We want to hit all the minors of K5 and K33. B, what is the objective? You can also rephrase this problem as a vertices which hits all the minors of K5 and K33. So if I delete an edge, I mean, I can make only life harder, easier. If I contract an edge, I can only make life easier because now rather than picking 2 vertex, I can pick 1 vertex, right? So this only makes the problem easier. You should not be making problem harder. But dominating set problem is not closed undertaking minors, because if I delete an edge, I might need more vertex now. So solution size can increase. So dominating set is not minor closed parameter. But is dominating set contraction closed? Means if we just allowed operation is contraction, can dominating set size increase? No, because only thing which you allowed is contract. So if this vertex was taking care of many more people, now if I contract, it can take care of this plus this. So if I just apply contraction operation, then the dominating set of the input graph will never increase. Okay? So we will see some of these things in this lecture, okay? And how these things are formulated and this. Okay, so let's start with the party problem. So what is a party problem? So you want to invite some colleagues for a party, okay? And what you want to maximize is the total fun factor of the invited people. And the constraint is that everyone should be having fun. So you want to invite some colleagues for a party, and the total fun factor, this is what we want to maximize. We want to select a set of people such that the fun factor of the party is maximized, and there should be no one who should not be having fun. So that's a very simple thing. Never invite your boss, because if you're going to invite your boss, I mean, then there's very less chance that you're going to have some fun. Okay? So do not invite a colleague and his direct boss at the same time. I mean, if your boss is somewhere up, he may not even know you, so you don't have to worry about that. Exactly. Right? For example, I'm sure we all know the director, but I'm sure director doesn't know many of us. So it's okay if we both are there. He may not even know that we belong to the same institute. Okay. So let's phrase this problem in a following way. So if we can phrase this problem, because there's a direct descendant relationship. So you are given a tree, and everyone has, like, if you invite this guy, he will contribute to fun factor of 2. If you're going to invite this guy, he's going to contribute a fun factor of 6. And basically, what we are asking for, what is the maximum size, what is the independent set of maximum weight of this tree? This is what we want to do. This is what we are interested in. So the problem, this party problem, can be restated in a graph theoretic term, is that we have been given a weighted tree, and you want to find a maximum weight independent set of this tree. Is the problem clear? This is what we are going to make, don't worry. And this is what we will make at least for the next 2 days. Okay? Okay, so for example, if we pick all this seems the largest maximum weight independent set, like 4, 4, 6 plus 6. Okay, this is a very, so now if I gave you this problem, I'm sure you have seen this problem in your normal algorithm, school text. So let's just do that algorithm for repetition. Something which you know, you feel good that, okay, at least I understood 5 slides. Okay, so what is the dynamic programming paradigm? We want to solve lots of subproblems, and we want to get a solution using these small subproblems or subroutines which we solve. So to solve our problem, let TV denote the subtree rooted at V. For example, this is a subtree rooted at this 5 guy, looks very unhappy guy, and this 2, everything, right? So basically, and we are going to store 2 values at every vertex. What is the 2 value? At A of V, we are going to store maximum weight independent set in this tree TV. And what is BV? Is a maximum weight independent set in this TV if we decide not to include V. So at every node in this, we are going to do dynamic programming from bottom up, from leaf to the root, just fix any vertex arbitrarily as root. And at every stage, we want to keep the following 2 information. What is the maximum size, maximum weight independent set in the subtree rooted below, which contains V, and what is the maximum weight independent set for subtree below, which does not contain V. Okay? And what is our goal? Is to determine AR for the root R, because that is the guy who is going to store the value of the maximum weight independent set.
So why? So A is inclusive of B, right?
Yeah, we could.
So you don't want to determine AR for R, you want to determine maximum of AR comma BR for R.
What?
I mean, how is AR the goal? You want to determine max of AR comma BR, right?
But AR, what is AR? Is a maximum weight independent set in TR.
AR includes BR.
It,
I mean, so these have.
I have in my AV, do I ever say that it has to include V? I just say that it is. Huh?
I thought you missed it.
No. No, I have not missed it.
So then B is subsumed in A, right? I mean,
But you need this as a help function. You will see why in a minute.
for filling in the table.
Exactly. This is it. Okay. So I'm not wasting too much time. So this is a method. Assume that V1 and Vk are the children of V. So we are going to use the following recurrence. What is B of V? Well, if I have a, if I have a BV and my children, and if I decide not to include this vertex in my independent set, then what should I do? okay, let's compute the maximum weight independent set here, 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 and just take the sum, because an independent set here and an independent set here does not interfere. So do you agree to this recurrence? B of V. Okay, very nice. Now that you have computed BV, now what you have to compute? AV. So AV, as C says, there are two possibilities for this vertex. Either I'm looking for an independent set that does contain V or that does not contain V. If it does not contain V, then I have computed that in B of V already. Now suppose it decides to contain V. But if it decides to contain V, then it cannot contain its children, right? V1, V2, V3, Vk. But I have stored a maximum weight independent set below without its children in BV. So I add the weight of this because I decided to add this vertex to my solution, and I added the weight of each of these people. So, okay, and I just take the max of these two. Okay, leaves are trivial, right? For the leaves, it is a single vertex. So what is AV is this, and what is BV is 0. So is the DP clear? And do you agree that we can do this in linear time, going from bottom to top? Okay, very good. Huh?
So AV, maximum of VV, WV plus summation of, so that should be AVI or
This is BVI, no? Because BVI is guaranteed not to include VI. Because if I decided to pick V in my independent set, can I take any of my neighbors in my independent set? No. And that is why this values. Okay? Agree? Okay. Very nice. Okay, so rather than talking about this maximum weight independent set, for now let's forget weights and we are interested in maximum cardinality independent set. But now we want to try to solve this problem for an arbitrary graph G, not on these trees. I mean, trees was easy. But let's see how this method can be generalized for an arbitrary graph. Okay? The idea is to again to perform dynamic programming, but this time instead of going from leaves to the root, we go via what I call separating set of vertices. I'm sure you don't understand this jargon yet, but you will understand in a minute. So something called separating set of vertices. Okay? Okay, so but we want to do the same thing for an arbitrary graph. Okay, how we are going to do, I'll show you in a minute. So we fix an ordering, okay? We fix an ordering of vertex, V1, V2, V, some arbitrary ordering, let's call it rho. So it's an arbitrary ordering of the vertices, okay? For a j in 1 to 2n, what are we going to say? So what is Vj is going to be V1 to Vj, j. So basically first j vertices. Now, okay, let's define another thing. And what is going to be called boundary of Vj? What is the boundary of Vj? Is a subset of vertices of Vj adjacent to vertices outside Vj. So for example, look at, this is my Vj, and what is the boundary of this? Those vertex which has some guy outside Vj. We'll see an example in a minute. Okay, so look at this example. Look at this, suppose my sigma is A, B, C, D, E, F, G, H, I in this picture. And now say for j equal to 5, so it is A, B, C, D, E. So A, B, C, D, E. So what is its boundary? And we denote the boundary by delta Vj. So those vertices which has a neighbor outside. So which has a neighbor outside? D has a neighbor outside, E has a neighbor outside, but ABC does not have a neighbor outside. So the boundary of this vertex is D. Okay? Just few definitions. So I had an ordering of the vertices. By Vj, I mean first V1 to Vj, and by boundary, I mean those vertices which has a neighbor which is not in Vj, like Vj minus V minus Vj. Or if you do not like this, delta of Vj is nothing but n of V minus Vj. It's a neighborhood of vertices which is outside. So this is, okay? These are like boundary people. What I mean by boundary, these are the people who are going to pass information to the world, okay? These are the people who are going to pass information from this part of the graph to this. This is, ABC is not seeing F, G, H, I, and that is the kind of property we would like to use.
why should it be equal?
What do you mean by equal?
Vertices which are not
It is exactly equal. It is exactly equal.
There might be vertices outside of VJ. They might
So what is the neighborhood of the vertex outside? Those vertices which it sees here. That's it. So that is the basically definition of delta Vg, right? Okay? Or if you do not want to get confused, it's those vertex in Vj which sees someone outside in the world. Okay? And here is an example. Okay?
maybe the right thing to say there would be n of v minus vj intersection the
No, what do you mean by intersection?
intersection the nodes which are lying here, because the neighborhood of those vertices could be lying outside, right?
Lying where?
The outer world itself.
N of V minus Vj can only belong to Vj. Because by definition, N of V minus Vj does not include vertices from V minus Vj. It's not closed neighborhood, it's an open neighborhood. No? Confusion, confusion, confusion. N of x is those y such that xy is in the edge, but it does not contain x. So when I say n of v minus vg, look at all the neighbors without v minus vj. So all its neighbors can only go to vj, right? So please don't get confused. It's set those vertex which sees outside. Please, that's all that is required. Now, why am I so much interested in this object? Now notice that every path from v in vj and u not in vj contains an edge with one endpoint in vj other and other in this. So what is the meaning? So any path which starts from here to here goes from this part of the world to this part of the world must intersect these boundary vertices, right? Because I start from somewhere here and I want to go to the world. It's very simple. I'm a vj here. Here are my boundary people, and here is outside. I want to go from here to the world. Now I cannot, and this is the only people who has edge outside. So if there's a path from x to y, it must include some vertex from here. And this is why I use the word delta Vj separates Vj from the other vertices of G. What is this? So if I delete this vertex from the graph, boundary vertex, there is no edge from here to here, right? For example, if I delete DE, is there an edge from ABC to FGHI? No. And that is basically, this is what I meant, separating set of vertices, right? So boundary of my instance kills, if I delete those vertex, it kills all the paths starting from left to the right, right? Is this definition clear? Because this is all that we need. And after that, it's going to be simple life. So please look at this, convince yourself that whatever we said makes some sense. Okay. What is our goal? So for an ordering sigma, let T sigma denote the maximum size of the boundary, right? So fix a sigma. What is T rho? Is a maximum cardinality of the boundary. For example, here if I take ABC, what is the boundary size? What is the boundary size here? What is the boundary of AB? Is 2. What is the boundary of AB? It is 3. What is the boundary of AB? No, sorry. What is the boundary of A? Is 1. What is the boundary of AB? It's 2. What is the boundary of ABC? It's 2. What is the boundary of ABCD? It's 2. No, it's C, B, D both, right? So it's 3. Now what is the boundary of ABCDE? We just still, if you do it. So what is the number we got up until now? Largest is 3. So T rho is maximum of this boundary size. So for that particular example, you can check it for yourself. It is 3. Now what are we interested in? We want an algorithm for maximum independent set running in time 2 to the power big O of this boundary size and n to the power big O of. That's a goal. Okay, we will do exactly what we did for the party problem. Don't worry. This lecture we will only do party. Okay. Okay. So this is what our goal is. Let's change the track and do something else for a minute. We'll come back. Okay. I want to make life even more simpler. So this is what our goal is. We will achieve this goal at least in the next 15 minutes, I promise. Okay. Yes, please ask.
So in this case, who gives these?
Who gives this?
Sigma? I mean, this is something you came up with. Is it for every order?
Yeah, so like suppose if I have been given a fixed ordering sigma, suppose you gave me some fixed sigma, I will give you an algorithm for this particular sigma which will run in this time. There are lots of questions to be asked here, and you are right. But suppose for a moment that someone gave you the sigma. It doesn't matter, you start with an arbitrary this thing. I mean, if you can come up with sigma where this t rho is smaller or something, you are going to make progress. But we will get to that. For now, let's just suppose I have been given a sigma. Can I come up with an algorithm which for maximum independent set which only depends on the largest boundary size? Agreed? Okay. Okay. So let me define what I call t-bounded graph. What is a t-bounded graph? It's a graph. Okay? It's just a normal graph. And you will see why I am so much interested in this graph. So it's a graph. Maybe this is a bad chalk. And I call some t vertex. Let's call them x1 to x2 to xt, special vertex. These are my special vertex. Okay? I'm going to call this graph where you have a graph and I have assigned t vertex or at most t vertex. These are my boundary vertex. So I have colored them, say for example, this is it. Now, these are the special vertices. So if you look at their ordering, I am trying to call the vertices which is on the boundary as special vertices, right? So I am trying to give a definition of t-bounded graph by saying, okay, here this boundary is coming very naturally. Let's just forget this for a moment. Let's define a notion itself of a t-bounded graph. And what is that notion of t-bounded graph? I start with an arbitrary graph. I call some t vertex and say, hey, these are my special vertex. And I will tell you how to do things with this t-bounded graph in a minute. But that's a basic definition. For example, this is my graph, and this is the x, and these vertices are called, these are my boundary vertices. Okay? So think, if you are not able to think properly, then think that in this ordering, these special vertices are precisely those vertices which will be our boundary vertices. Okay? So I have defined for fixed. You start with any graph. Okay? You start with any graph and you pick some t vertex. I said, oh, for this graph, these t guys are special vertices. These are called bounded graph. So it's a. Huh? Okay, wait. There's nothing called. This is just to show you why are we trying to do this semantics. So basically what is, you know this, what is it? This is, let's call this class of all graphs. Okay? I'm going to define psi t, which is basically g, comma, some x subset of vg, okay, cardinality of x less than equal to t. This is my family of all t-bounded graph. How it is given? A graph and some specified set of vertex, at most t of them. So this is a pair. Think of them as a pair, right? It's not anything. Graph is just a graph. But think of a t-bounded graph as a graph and a set x, which is a subset of my vertex set, which I'm going to call special. It has nothing to do with what we did before anything. Just take it as a face value. I will tell you what we can do with this, and then we will connect this to whatever we were trying to achieve later. Okay? Like, so for example, look at this graph, Vj. I can think of this as look at the graph induced on Vj, and I can define my special as this boundary vertex. So G, Vj is my pair of t-bounded graph. I can write this graph in the language of my t-bounded graph, where I take a graph and set of vertices which is in the boundary as boundary. But for now, just forget it. Just imagine this is my class of graph, and let me tell you what we can do with this class of graph. Okay? Is it too abstract? Is it too abstract notion? Forget this. This is an example. This is what I say. This is. Don't read this line. This was my bad. Don't read. Okay. Okay. So Are you happy with graphs? All class of all graphs?
Yeah, that's fine. See, when you say X is called the boundary of G.
I define, I call it, I fix, look at, this is what I call, it's a pair G comma X. I call, these are my special vertices.
So my question is, boundary vertices are defined with respect to some J, right?
No, that is a completely different definition, don't worry about it. It's a different boundary.
Oh, the third different boundary. Confusing part.
Just remove this line. Should I do edit? LaTeX edit, I have LaTeX source, I can do.
So this is a different boundary, huh?
Yes. Okay. Okay. So just forget it. I will tell you what you can do on what kind of operations I plan to do on this graph. And trust me, if you just listen for 10 minutes without asking too many questions, by that time you will have understood whatever it means. Okay. Okay. I just have 10 minutes, so I have to do slightly. Okay. So this is called boundary graph. So it's a graph and some special vertex which I have called. These are my boundary. Or think of this. These are going to be our action-packed objects. Okay. So I want to do this generalization of dynamic programming table. So what we have stored now, for every subset S of the boundary, T of S is the size of the largest independent set I. Let's read this, such that I intersection X equal to S or minus infinity if no such independent set exists or something. Okay? So what is my goal? I want to do kind of dynamic programming table which we were trying to make before. Now what I want to say that look at every subset here and we are going to store T of S. What is T of S going to store? It is the size of the largest independent set I, such that I intersection with this boundary is exactly equal to S. It is possible that, for example, if I take this, there is no independent set containing x1, x2 because there is an edge. In that case, I put minus infinity. So this is the table which we would like to fill. That's a goal. What is our goal? For every subset S of the boundary X, T of S is the size of the largest independent set I, such that I intersection X is equal to S or minus infinity if no such independent. This is my goal. What? Yeah, I want to say that this cannot be. 0 means that it is still extendable. Minus infinity means it cannot be extended. It doesn't matter. I mean, you can just keep any boolean. Okay, now let's fill this table. I have filled, see, I have written the whole table. Let's fill this. Suppose this is my graph and I want to fill this table. What is T of phi? 4. 1, 2, 3, 4. Agreed? Oh, come on, this is too cheating. But if I told you that find a maximum independent set whose intersection with X is empty, it doesn't, then you have to find independent set here. So 1, 2, 3, and 1, 4. So 4. Okay, let's look at anything else. Can there be an independent set containing x1, x2, and x3? Because there is an edge between them. So we cannot extend this to an independent set, so minus infinity. Let's see some other value. What about t, x2, x3? x2 and x3. So now if I pick x2 and x3, clearly these guys are not allowed to be picked. And from this triangle, you can only pick one. So the largest independent set containing x2 and x3 is 3. Agreed? I'm just filling the table. Similarly, you can fill other table. You can verify for yourself this is correct. At least the idea of filling the table is okay. How you fill it is not important, but is the idea of filling the table is that part clear? Okay, but I mean seriously, I mean who cares about this? Now let me introduce some new things which you can do to this T-bounded graph. The allowed operations. What you can do to this graph, you can add a vertex xi not in X to X. The vertex xi can have arbitrary neighbors in X, but no neighbors here. Okay? So what are you allowed? You are allowed to introduce a new vertex and say, hey, but this vertex can only have edges to this special vertices. Okay? Then this operation is called introducing a vertex. Okay? Introducing a vertex. Okay? But no other neighbor. So this guy cannot have neighbors anywhere else. Okay? So for example, we have introduced x4 here. x4 came, it added edges to this. Now we want to update the table. So suppose you had a table without this. Now you did the following operation to my graph. You added some new vertex and maybe some edges here, but this guy has no edge here. Now how can we now update our new table for the new x, right? Okay, so suppose, so now introducing, updating the table T. So you had a table without this new vertex introduced. Now you have put this new vertex into this boundary. How are you going to update this table? Suppose xi was introduced into x. Here we introduce x4 with closed neighborhood here itself. We update the table T as follows. What is the new table T of S if xi does not belong to S? Now what is saying that, look, the newly vertex which you have added, I'm looking for the largest independent set in this particular graph. So now think what happened to this graph. So here you have x, you have added some new vertex and C is somewhere here. Now you want to update the table for this. So you say, if for some subset here which we are seeking a solution, if it does not contain xi, then whatever may be the largest independent set, because xi is boundary. So you are not allowed, if xi does not belong to S, xi is not allowed to be part of the independent set, because intersection with the boundary is exactly. So you have already stored before, so just keep this value. Now if xi is in S, okay, suppose xi is in this S, but this S has some edges, like some S. Like S contain xi and one of its neighbors. Clearly this cannot be extended to an independent set. So put minus infinity. This is what it is, S intersection n of xi. Otherwise, what is this? I said, okay, xi is going to be part of the included. Now xi has all the neighbors, xi here, and this is an independent set. So I said, okay, we are going to put xi and going to find the largest independent set in 1 plus t of S minus xi, which we have already computed. That's it. So this is how we can update the table. Given a table for the T boundary graph, if we introduce a vertex v, then we can update the table in this way. Is this updation clear to all of you? No? Yes? All of you look very droned. Is this correct?
When you introduce a new vertex, you don't declare a special set.
No, I call my new special set is old special set union this guy. This is what I call, right? Look at this picture. New x becomes the old x union the new guy, right? So when we introduce what we say, we introduce this vertex, we say this is also our special vertex. This is also our labeled vertex, but with an extra constraint that this newly added vertex can only have neighbors here. It cannot be seeing anything here, okay? So this is very local to this boundary, and that is why this updation is perfect.
So if xi belongs to S,
Yes?
the solution that is
We are looking for a largest independent set containing S such that intersection of S with the boundary is exactly equal to S. This is what our,
why should it be minus infinity? It's 1, right?
no.
No.
If x has some, look, if I have started with S where I have xi and its neighbor, it can never be, it's already the edge. If graph induced on S itself has an edge, can you extend it to an independent set? Look, if you have, if I have a S, if I have a xi and some y, there's an edge. Can you extend this to independent set?
This is no longer an independent. Xi belongs to S, the solution.
Yes, and S intersection n of xi is not equal to empty set. So S not only contains xi, it also contains one of its neighbors. It means there is already an edge in the graph induced on S. So this can never be extended. Okay? Okay. Now let's do another operation. What is called forget operation. So now what is forget? It's very simple. You pick some guy and say, now you are not a special anymore. Okay, so I said, just get out. I'll kick him out of the X. So for example, I kicked X4 into this. So I just called that this is no more a special vertex. So I just kick him inside the normal. So now our boundary has reduced, shrunk. We should still be able to update. Okay? Now let's update the table in the case when we forget some vertex. Look, forgetting xi here, means we forgot x4. Now look at S. Look at the largest independent set containing S. Look, in this case, graph has not changed. So largest independent set here, either it contains X or it does not contain X, like does not contain this guy. So this is why we wrote max of either the X itself or T of S union Xi. So this is why we put minus infinity, so that whatever number you put is larger than this. Okay? So we can update this. Agreed? How many of you have understood this DP? Seriously? Okay, great. 50% of you understood. I don't care beyond. But we are done now.
No, I don't.
Okay. So what you did not understand? Look, let's go back to this picture. Now, we had x4 here. Okay? Now we forgot this. So we said, no more you are a special vertex. So we just moved him to the inside and forgot his name. So you are just a normal vertex. But I know it was x4. Now we want to find T of S. We want to keep this table, updated table, only for this set from which we have kicked out x4. So now I'm writing a recurrence for this. I say, hey, look at this largest independent set. Largest independent set, this is my boundary. It contained some x4 before. Look at the largest independent set containing this S. Either it contains x4 or it does not contain x4. But in the table below, I have the largest independent set containing this union this, and also for the small set. So this is why I took max of this.
No, how do you have it for the small set which does not?
Because I have table for all of these subsets.
Oh,
I have a table for all this, then we can update the table for smaller size subset because I have computed everything before. So this is why just this recurrence. So I just look at the two values. So if the size of this size was t in 2 power t time, we can update this table. Is the algorithm clear? Okay. But we wanted an algorithm for some permutation and blah, 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 blah. And what did we achieve? Nothing. Okay. But let's see how these two little operations imply algorithm of our kind. Think. It is just 2 lines. Okay. Here's my sigma. V1, V2, Vn. Okay? Okay. Now let's look at some Vi. Look at the graph induced on Vi, and our x, as I told you, is going to be this. This is what it is. Suppose I have in table for every subset here. Okay? Suppose for singleton I can compute, right? Singleton, it's only one which goes out. Now, when we look at, let's look at Vi union Vi plus 1, because that is the next step. So we have computed things here. Now we want to increase this, and we want to compute this table for delta Vi like sequentially from left to right. Whatever we have computed, use for next we want to compute using whatever we have computed. This, using this, this, using this, this, and we want to apply to some of the operations. Now notice what happens. Okay? Look at this up until now. These are the people who were seeing in the world. Okay? It might be that many of them were seeing Vi and this world. It is possible that Vi also sees world. So when I make next, for the next, look at the boundary. I claim that, let's say if you agree to this, delta of Vi plus 1 is contained inside delta of Vi union Vi plus 1. Do you agree to this? I said, look at the boundary of the new graph. It is contained inside old boundary and the newly added vertex, right? Because look, anything which was seen before can only be seen, and in the worst case, now you have ordered Vi plus 1. Who could be seeing more object? Agreed?
Whatever lies beyond Vi plus 1, we
Already have been seeing before, but it's possible that Vi plus 1 also sees some people. So delta of Vi plus 1 is contained inside this. This is all that I'm saying. Is this clear to all of you? Right? The boundary of graph Vi plus 1 is the old boundary plus the single subset, because it could happen that all these 3 people were only seeing Vi plus 1, and now because Vi plus 1 has gone inside, actually it can shrunk. It can shrunk very badly, right? But I'm just saying that it is contained inside this. Okay? So now what I think is very simple is that, okay, I have this Vi. Okay, so I have Vi. Think of Vi plus 1 as introduce, get the big thing. And now, whichever is in delta Vi plus 1, whichever is delta Vi minus delta Vi plus 1, forget one after another. Right? So what I do, how do I update a table? I said, okay, I have a delta Vi contained. Now I think of this as a bounded graph with this. I make a new bounded graph with Vi plus 1. Right? New bounded graph with Vi plus 1. I compute its table. But this is not equal to delta Vi plus 1 because there are maybe some vertex which is not part of. So for example, if you first grow and then be one by one, you forget till you become delta Vi plus 1, and then you're happy. Right? And each of this sequence in between is like some polynomial, who cares? So by using our forget and introduce one by one at every time, so you might have to do many sequences. For example, we first get a table for delta Vi union Vi plus 1 by introducing. We get this table. But this is not equal to delta Vi plus 1. Maybe, for example, these are the vertex which we need to lose. So we said, okay, this is not equal. Let's lose one vertex. Let's make the symbol of one guy bad, like non-symbol guy. We got something more. Oh, there's still people which is not in delta Vi plus 1. Forget till you hit this. This is an algorithm. Now this algorithm runs in time. Let's see. Okay, so I went to the drawing board, and I gave you an algorithm. So the running time of this algorithm is actually, agreed? This is the running time of this algorithm, right? Because every table, honey, there's n to the power big O of 1 which can take care of constants. Just in case. Okay? Okay. So it's a tree with lecture, so you should take something away. So this is my last slide. For an ordering sigma, T rho is this. So now I define what is called vertex separation number of graph. What is the vertex separation number of graph? Is minimum over T rho, where rho is a permutation of G, right? So the best thing will be that I find a permutation for which this boundary is maximum of this boundary is as small as possible. So this is what is called vertex separation number of graph. What is the vertex separation number of graph? It's minimum of over all permutation. So basically it is min of max for each permutation, right? Is this clear? Definition clear? And what we have shown is that we can find a maximum independent set in the graph in time 2 to the power vertex separation number and some big O, don't worry, if the corresponding permutation is given. So if you give me the corresponding permutation, then we can do these things. Okay. So 2 important questions are not answered so far. How to find a good permutation? How to find a permutation which minimizes this? This is a good question. While the vertex separation number of tree can be arbitrarily large. So if you take a binary tree on n vertex, please think in the break that its vertex separation number can be roughly like log n, right? But the algorithm which we use for trees and this vertex separation number, they were same. Were they anything different? In the tree, we kept this value AB and BB. What were you keeping? The largest independent set with him or without him. Now, for this graph, we said largest independent set containing a subset from this because our boundary was large. So basically, in that sense, it is a similar algorithm like trees. So algorithm was like trees, but the trees can have a vertex separation number like log n. So in what follow, we will provide you answer tomorrow, is that we can make use of what is called tree decomposition and tree width, which will have good features of both this. A, it will be computationally tractable, and B, algorithm will be exactly the same. Okay, any question? because I think this is a very good time to stop. So you fix a graph. You go, so for each permutation you have some maximum boundary.
Can't you always give an ordering in which every node between vertex and all the edges going back?
You click. That's the only example, but there could be a graph which could have this small.
That's what makes it a big deal.
Mhm.